Okay, in example 2, we take a look at another example where we apply Green's theorem to calculate a double integral instead of a line integral. So in this line integral, again, let's make a note of the two components p and q. So if you take a look at the way the vector field is set up in this problem, the p and q components are a little bit more complicated than in example 1. And so trying to calculate this line integral is either very complicated or impossible to calculate by hand. Okay, so we're going to apply Green's theorem. Right, so again, we have to describe the region R. And in this case, because it's an annular region, right, so it's half of an annulus, and it's circular in shape, so we're going to use polar coordinates. Okay, so how do we set this up in polar coordinates? So we have, in polar coordinates, we have theta and we have r. So in terms of the angle, we start here at the positive x-axis, and we rotate around and end up here. So theta goes between 0 and pi. And for r, so you start from the origin. The inner circle has radius 1. So that's where the annular region starts, and then it ends here at the outer circle, which has radius 3. Okay, so r goes between 1 and 3. Okay, so now, just like the previous example, we have to calculate some partial derivatives. Right, so the partial of q with respect to x. So this is just, you think of y as a constant, so this goes away, so we just get minus 2x. And then the partial of p with respect to y, so we're thinking of x as constant, so this term goes away, and so this is just equal to 2y. So now q sub x minus p sub y is just minus 2x minus 2y. So notice how in calculating these partial derivatives, the setup for the double integral is much simpler than the original components for the vector field. Okay, so now we're ready to apply Green's theorem. So again, instead of calculating the line integral directly, Green's theorem allows us to replace it with a double integral over the region R of the partial of q with respect to x minus the partial of p with respect to y. And we have everything set up, right? So in this case, we're working in polar coordinates. So theta goes between 0 and pi. R goes between 1 and 3. Here, we do qx minus py, which is written out here. But we're working in polar coordinates. So as a reminder again, we have to make a substitution, right? Because we don't want to calculate in terms of x and y. We need to calculate in terms of r and theta. So we have the substitution x equals r cosine theta, y equals r sine theta. So that's the substitution for polar coordinates. Okay, so we have minus 2 r cosine theta minus 2 r sine theta. And then also, don't forget dA is equal to r dr d theta, right? So there's this extra r when working in polar coordinates. So we have r dr d theta. Okay, so let's calculate the double integral. Let's clean things up a little bit, right? So r times r is r squared, and I can they both have a minus 2r here, so we can just factor that out. So minus 2r squared, and then what's left over is cosine theta minus sine theta. dr d theta. Okay, so in this problem, once we've written in this way, notice that r is completely separated from theta. So we can actually simplify this this double integral, right? So the idea is that since r is separated from theta, we can separate the double integrals also. Okay, so what do I mean by this? And one other thing before I separate the integral, right? So the limits of integration also don't depend on r or theta, so that's also important. So let me backtrack a little bit. So since r is separated from theta, and also the limits of integration don't depend, so they're just constants, right? So everything here is a constant. Don't depend on r or theta. We can separate the double integral. Okay, so what do I mean by this, right? So here the integral with respect to r goes between 1 and 3. So what are the things for r? You have this minus 2r squared, right? That has already been separated from this thing. And then I can also separate the dr. So that's one calculation. And then the other calculation is for theta. Theta goes between 0 and pi. You have cosine theta minus sine theta d theta. Okay, so we can separate the integral like this and calculate them separately, right? So again, notice that this doesn't depend on theta, so we can just think of this as an ordinary integral, and this doesn't depend on r, so again we can just think of this as an ordinary integral. Okay, so the antiderivative here is minus 2r cubed over 3 evaluated from 1 to 3, and then times the antiderivative here. So the antiderivative of cosine is sine. The antiderivative of sine is minus cosine. So minus minus becomes a plus, evaluated from 0 to pi. Okay, so now we just calculate, right? So plugging in 3, you get minus 2 times 3 cubed over 3 minus, plugging in 1, yeah, I don't need the bracket there. Plugging in 1, you get minus 2 times 1 cubed over 3, and then times, plugging in pi, you get sine pi plus cosine pi, and then minus sine of 0, and then minus also because it's the minus distributes, so this is also a minus, so cosine of 0. Okay, so what do I get? This is 3 cubed is 27. 27 divided by 3 is 9. 9 times negative 2 is negative 18. This is minus minus becomes a plus, so plus 2/3 times sine of pi is 0. Cosine of pi is negative 1. Sine of 0 is 0. Cosine of 0 is 1, but you have this minus, so it's a minus 1. Okay, so what do we have? What is this? Negative 18 plus 2/3 as a fraction. What is this? Negative 52/3 times is negative 1 times negative 1, so that's negative 2. Okay, so this is equal to hold on, I think I've made a mistake. This should be I mean, this comes out to be positive. The answer should be negative. So let's go back. Okay, so here I had minus 2r times cosine theta minus 2r times sine theta, and then I factored out the minus 2r. So when I factored it out, this should have been a plus. So this should have been a plus here. Okay, so let's fix that. This should have been a plus here, so that when you take the antiderivative of sine, this should be a minus. That should be a minus. It should be a minus. And then minus minus, this should be a plus. Okay, so what does that mean? Cosine of pi is negative 1. Negative minus minus 1 becomes a plus. Okay, so this should be a plus, and this should be a plus. So this should be a plus. And then, okay, so now finally, now we have the right answer. So this is minus 104/3. And okay, so here we applied Green's theorem, and the answer is negative 104/3. So going back to the beginning again, I mean, so the calculation of the double integral here is a little bit more complicated than before, but however, I'm not going to even try to do it. Trying to calculate the line integral is going to be much more complicated, right? So first of all, the curve C now has 4 components, right? So this would be C1, C2, C3, C4. Right, so 4 components, so 4 separate line integrals. And again, the P and Q components here are much more complicated functions. So this line integral is going to be much more complicated to try to calculate directly. So it's much preferable to use Green's theorem in this problem.